Ever wonder why you see triangles everywhere? I mean, look at a bridge, a roof, even the frame of a bike. They're all packed with triangles. And there's a really good reason for that. Triangles are incredibly strong. But here's the cool part. That strength doesn't just come from the metal or the wood. It comes from the pure, simple math of the shape itself. To really get why, we've got to go back to basics.
All right, so here's our game plan. First, we're going to nail down the absolute basics. What exactly is a triangle? Then, we'll dive into all the different types you can find. After that, we get to the golden rule, the one thing that's true for every single triangle. And to wrap it up, we'll see how that one rule helps us figure out some pretty cool stuff, like exterior angles.
Okay, let's jump right in. First principles, defining the triangle. Yeah, we're starting with the absolute basics, because you gotta have a solid foundation, right?
So here's the official textbook definition. A triangle is the union of three line segments that are determined by three non-collinear points. Whoa, okay, non-collinear? What does that even mean? It's actually super simple. It just means the 3 points can't all be lined up in a perfect row. I mean, think about it. If they were, what would you get? Just a straight line, right? You need that third point to be off to the side to actually form a triangle. And this is what it looks like in practice. You've got your 3 points, A, B, and C. You connect the dots, and boom, you have triangle ABC. Now, mathematicians love a good shortcut, right? So instead of writing out triangle ABC every time, we use that little symbol, the delta symbol. So when you see that, you just read it as triangle ABC. Easy enough?
Okay, let's break down the parts of a triangle, kind of like its anatomy. The corner points A, B, and C, those are called the vertices. The lines that connect them, well, those are just the sides. Make sense? Then you have everything else. Any point floating around inside, like D, is in the interior. Any point outside, like F, is in the exterior. And what if a point is sitting right on one of the sides, like E? We just say it's on the triangle. Getting this vocabulary down is super important for everything that comes next.
All right, next up, the types of triangles. Because not all triangles are created equal. We know what a triangle is, fundamentally. But now we're going to see how we can sort them into different families. And it really comes down to two main ways of classifying them, by their sides and by their angles. So first, let's talk about sides. If a triangle has 3 sides that are all different lengths, we call that a scalene triangle. Now, if exactly 2 of the sides are the same length, it's an isosceles triangle. And you see those little tick marks on the sides? That's a little geometry code that means these sides are equal. Finally, if all 3 sides are exactly the same, you've got the superstar, the equilateral triangle. Okay, that was sides. Now let's classify triangles by their angles. If all 3 angles are kind of sharp, less than 90 degrees, that's an acute triangle. Think acute little angle. If it has one big, wide-open angle, more than 90 degrees, that's an obtuse triangle. If it's got that perfect 90-degree corner, like the corner of a piece of paper, that's a right triangle. And if all 3 angles are exactly the same, we call that equiangular.
All right, time to put this into practice. Let's try a little example. Imagine we have a triangle called HJK. We're told that side HJ is 4 units long, and side JK is also 4 units long. And one more clue. The angle right at vertex J is exactly 90 degrees. So the question is, based on its sides and its angles, what kind of triangle is this? Think about it for a second.
Did you get it? Let's walk through it. Okay, so it has 2 equal sides, right? That makes it isosceles. And it has a 90-degree angle, which makes it a right triangle. So what do? We just combine the names. Triangle HJK is a right isosceles triangle. See? A single triangle can have a name from both categories, one for its sides and one for its angles. Okay, moving on to section 3, the golden rule. I'm not kidding. This next part is, well, it's maybe the most famous thing about triangles. This is the key that unlocks almost everything else. Now, before we get to the rule itself, I want to let you in on a little secret, a tool that geometers use all the time. It's called an auxiliary line. Basically, it's a helping line that you can add to a diagram to help you prove something. It's like a secret weapon for finding hidden connections in a shape. But you can't just go drawing lines wherever you want. That would be chaos. There are rules. Any auxiliary line you draw has to be justified by a known geometric principle. For example, we know there's only one straight line that connects 2 points. or that an angle has exactly one line that can split it perfectly in half. These rules make sure our proofs are legit and built on solid logic. And all that leads us here, to Theorem 2.4.1. This is the big one. Are you ready? In any triangle, I don't care if it's big, small, acute, obtuse, whatever, the sum of the three interior angles is always 180 degrees. Every single time. No exceptions. 180. That's the magic number. Burn it into your brain. For any triangle on a flat surface, this is the rule. And trust me, knowing this one simple fact is a total game changer. Now here's something cool. Once you prove a really big theorem like that one, other little truths just kind of fall out of it. They're called corollaries. Think of it like this. The main theorem is a big earthquake, and the corollaries are the logical aftershocks that follow.
So let's check out our first corollary. Remember that equal angular triangle we talked about, the one where all three angles are equal? Well, if they all have to add up to 180, and they're all the same, what does each angle have to be? Yeah, you just do the math. 180 divided by 3 is 60. So every single angle in an equal angular triangle has to be exactly 60 degrees. See, it just follows directly from the main rule.
All right, let's put this all together in our final section. We're going to see how that 180-degree rule is even more powerful than we thought. Because it doesn't just tell us about the angles inside the triangle, it also unlocks secrets about the angles on the outside.
First things first, what is an exterior angle? Well, it's pretty simple. Just imagine you take one side of a triangle and you just extend it. Keep drawing that line straight out. The angle that forms between that new line and the next side of the triangle, that is an exterior angle.
So, on the left, you can see what one of these looks like at a single vertex. But check out the image on the right. If you do this at every corner, you find out that a triangle actually has a total of 6 exterior angles, 2 at each vertex, forming a pair.
Okay, let's zoom back in on just one exterior angle, the one at vertex C in this diagram. Now look inside the triangle at the other 2 angles, the ones at A and B. They're not touching our exterior angle, right? They're the ones furthest away. Because of that, we have a special name for them. They're called the non-adjacent or remote interior angles.
And this brings us to another awesome corollary. The measure of an exterior angle is exactly equal to the sum of the 2 remote interior angles. Let me say that again. The angle on the outside is equal to the 2 opposite angles on the inside added together. So in our picture, the exterior angle at C is equal to angle A plus angle B. How cool is that? And it all stems from that 180-degree rule.
So, let's finish off with a little challenge for you, a final brain teaser. Let's say you have an exterior angle that measures 130 degrees, and you know that one of its remote interior angles is 50 degrees. So, what's the measure of the other remote interior angle? Think about that last rule we just learned. The answer isn't a guess. It's a perfect calculation, all thanks to the simple, powerful geometry of the triangle.